To understand radio, we have to have an understanding of electricity, what it is and, as importantly, how to measure it. But that's easier said than done. But to start with then, we're going to look at how to make some electricity, if that's the right word, and from there we can lead on to understanding how to measure it and such like. Here we have some, they're just paper clips and a steel screw. Yes, that's right, it's a screw. And there's nothing very special about them, they're just standard pieces of gear that you'd find in most households. This device here I'm holding in my left hand is a magnet. This rod is magnetic, and if I bring the magnet in contact with the paper clips and the screw, we can see it's no surprise that they stick to the magnet. Well, as I say, there's no surprises there. We've all seen this being done before when we were children. Let's move that out of the way then. This device here is an ammeter. It measures amps. I know that because it has a large capital A printed on the screen behind it. And the little lowercase u in front of the A indicates that it's a microammeter. It measures millionths of an amp, microamps. And the way it measures it is that this central pointer, this needle pointer in the middle there, you can see its shadow being cast on the screen behind. If I don't show it to the spotlight, otherwise you'll get glare. But the only way I can make that centre needle, that red needle in the middle, move one way or the other is to either shake the meter, which doesn't do the mechanism inside any good at all, or I can pass a small electric current through the meter by means of these contacts on the back. Let's move that to one side. This is a coil, if you can see it. Yep, there it is. This is a coil of wire. It's one piece of wire that's been wound around and round and round and round and round and round this central former, a plastic former that's called a bobbin. It's been wound in a rather rectangular shape, and although there's quite thick insulation on the end of the wire where it comes out of the coil, the actual wire inside the coil, you can't see it, is much, much thinner. In fact, that's how thin it is. You can see it on the end of my fingers there where the insulation has been stripped off. If I connect this coil to the terminals of this meter and then move a magnet through in and out of the coil, let's see what happens. And now if I move the magnet in and out of the coil, we can see the meter needle deflects one way or the other. It's not only giving us an indication of how many milliamps of current are flowing through the coil because the magnet's going in and out of the coil, but the needle also shows us in what direction the electric current is flowing. And you'll notice it moves in exact accordance with the direction of the magnet. If I stop moving the magnet, the needle pointer goes to zero. No electricity is being produced. If I move the magnet to my left, the meter needle moves to the left of screen. If I move the magnet to the right inside the coil, the meter needle moves to the right. Left, right, left, right, left, right, left, right, left, right. Sounds like a soldier marching down the road, doesn't it? So by moving the magnet in and out of the coil of wire, whilst the wire is connected to the meter, we can see that electricity is being generated. And indeed, some 99% of the world's electricity, or 95% is it now, I'm not sure, is produced by means of moving magnets near coils of wire when the meter doesn't fall over. There we are. This is electromagnetic production of electricity. So that's shown us one way of producing alternating current electricity, AC electricity as it's known. But it hasn't really explained how it does it. How does the magnet work to make the electrons flow through the coil? Well, to find that answer, I've got another little demonstration for you, but don't go away because it's going to take a few moments just to set up. So, okay, here is a magnet. Now, you might not have seen, it's rather bigger than the last magnet we saw, and I don't know if you can see it, but it has N and S stamped on it. N, north, S, I don't think you can really see it, S, there we are, S, south. It has a north pole, as it's known, and a south pole, just like this planet has a north and south pole. So there are two parts to a magnet. Each magnet has a pole at either end. We're going to use this magnet here. We're going to use a piece of paper, and an image of the magnet is written on the paper, as you can see. I'm also going to use a couple of pens here, just a couple of biros, to support the paper's sides, and I'm going to lay the piece of paper directly over the magnet, and there it is there, it's directly over the magnet. Now what we can't see at the moment is this force field, this magnetic force field that's surrounding the magnet, or it's most strongly concentrated in the north and south pole area of the magnet. From this old salt cellar here, this old salt condiment, I've got some iron filings, and if I sprinkle them gently over the top of the piece of paper, some of them are going over the table as well, but what the hell. Now, some of the iron filings, let me just put that down, have gathered at the very strongest point of the magnet, which is down at the ends, at the poles. But if I tap the paper, you can begin to see a pattern emerging. Here are the so-called lines of force. Lines of force, the magnetic field. It's strongest at the poles, and it gets progressively weaker towards the middle of the magnet. But can you see there are definite kind of arcing lines forming here and here, where the magnetic field is flowing from one to the other pole. These are the lines of force, sometimes called flux. Try saying that when you've had a few too many jars of the black stuff, and it can come out rather different. But that's the magnetic field that's passing through the centre of the coil, and it is these lines of force, these lines of magnetic field, that are inducing or giving the incentive to the electrons in the coil of wire to move and make that meter needle deflect in one way or the other. So we've seen that if you have a magnetic field that surrounds all magnets, if you have a magnetic field and you make that magnetic field move near an electrical conductor, in this case a coil of wire, it can make the electrons in the wire move. It can produce an electric current. But it turns out that the reverse of that is true as well. If you already have an electric current and you make it go round and round and round a coil of wire, that too produces a magnetic field. So this magnetism and electricity are interchangeable. In fact, it's known as the electromagnetic force. Let me show you what I mean. So here we have a little setup to show you what it is. We've got a battery pack here. Here's a couple of AA batteries, and it's connected to one side of another coil. This is a different type of coil to the one we saw before, but in essence all coils are the same thing. They're one piece of wire. Here's one end of the wire and here's the other end of the wire, and the wire has been round and round and round and a hollow bobbin. As you can see, the centre of the cord is empty, and this lead here will simply be connected to this red lead, which goes back to the battery, and it allows the electricity to flow through the coil. This is a piece of steel. This piece of steel is not magnetic at all. I can't prove it to you, I haven't got those paper... Oh, yes, I have. Here's a paper clip. See, it doesn't stick to the paper clip at all, or the paper clip doesn't stick to the piece of steel at all. So this is not magnetic at the moment anyway. And I'm just going to place it in the entrance to the coil there, just a little bit, push it in a little bit like that, okay? Now I'm going to connect these two crocodile clips together very briefly, and the electricity, as I say, will come from the battery pack. There it is on camera. There it is there. It'll go round the wires, round the coil, and come back to the battery, completing the circuit, allowing all the electrons to flow. And we'll see the effect it has, particularly upon this piece of steel. Watch. The steel just moved in all by itself. And the steel will be held there. There it is, it's being held, it's being suspended in space by the magnetic field that's being created by the electrons flowing around the coil. So the electrons produce a magnetic field as they flow around the coil. If I now disconnect the battery, as soon as I disconnect it, if I can disconnect it, yes, that's it. Oops. Can't. That's it. As soon as I disconnect it, or the current stops flowing, then the piece of steel falls out and I'm dropping the cord, which doesn't help. So let's just do that piece again. The piece of steel is now sitting on the bottom on the table. If I connect the crocodile clips, whoops, it picks it up. And when I let go of the crocodile clips and stop the electric current, the electricity flowing through the coil, the piece of steel drops out because the magnetic field collapses. The coil no longer is magnetic and the piece of steel simply drops out again. There's a bit of a game you can play with this if you're very clever. I'm not claiming to be clever, but you can get the piece of steel to shoot right through the coil and come out the other side if you're quick enough. Oh, no, that wasn't quick enough. Well, I told you I wasn't very clever. Let's try it from the other direction, see if that works. Not quite. Oh well, anyway, not to worry, not to worry. So there you have a situation where you see for yourself that an electric current flowing through a coil creates this magnetic field that's strong enough to lift a piece of steel. Well, it's not a very big piece of steel, I agree, but then it wasn't a very strong electric current. It was only being powered by these two AA batteries. Don't expect too much. So, electricity and magnetism, electromagnetism, they are one of the same force. They're just different manifestations of the same force field or the same force.